As a wise man once said, magnets, how do they work? Is it
magic?
From where does the magnetic force come? Why some materials are magnetic and others are not? All of those things can be explained by the existence of one fundamental force surrounding us at all times. So, what is the definition of a magnet? A magnet is a material or an object that produces a magnetic field. Because of this, magnets can interact with other magnets or materials that can be magnetized. Magnetic force can pull and attract, or push and repel. This force is one of the four fundamental forces, interactions that can't be reduced to more basic interactions. We have gravity, allowing for anything with mass to attract other objects, bending the fabric of the space-time. Weak nuclear force, responsible for interactions between subatomic particles, changing quarks in protons and neutrons, and causing radioactive decay of atoms. Strong nuclear force, holding quarks together, forming atomic nucleus with protons and neutrons. And finally, electromagnetic force. It includes electricity and magnetism, both connected with each other. A moving electric field always produces a magnetic field, and a moving magnetic field always produces an electric field. It binds electrons and nucleus of atom together, forms chemical compounds, allows for electricity to exist. Also, electromagnetic radiation form waves, moving through the space as light, radio waves, and X-rays for example. Magnets, as all matter, are made of atoms. Negatively charged electrons and positively charged nucleus, so there is electrostatic force between them. But electrons and atoms as a whole are not stationary, and since electrons are charged and orbit around the nucleus, the magnetic force appears. Also, according to the quantum physics, electrons have angular momentum called spin. For simplification, we will consider atoms as a single object with a total angular moment, the combination of all movement. So, atoms are like microscopic magnets, and the direction in which a vector of their magnetic angular momentum points specifies which pole we can call north and south. Usually, poles are pointed in random directions and cancel each other. But some materials can be easily magnetized, depending on the number of unpaired and free electrons orbiting the nucleus. Now that we understand from where comes the magnetic force, let's take a look at some materials and how they can or cannot be magnetic. In theory, all objects can be magnetic. We just need to align their vectors in similar directions to create a magnetic field. Some materials, like a steel for example, on their own are not magnetic, but when we put magnet onto it, it starts to exhibit magnetic properties. Wood or plastic, on the other hand, are not magnetic, even if we put a source of magnetic field next to them. Actually, wood can be magnetic, but not in a way you may think. Wood is categorized as diamagnetic material. In fact, most of the organic materials, gold and water, are diamagnetic. Electrons in those materials form pairs, which on their own cancel each other magnetic vectors. When a magnetic field is introduced, they create own magnetic field in the opposing direction and start to repel from it. The force is just so small that it is unnoticeable. On the other hand, we have paramagnetic materials. In this case, some electrons are unpaired, so atoms can have magnetic vectors, pointed in random directions. Materials like aluminum, oxygen, and titanium, for example, don't exhibit magnetic properties. In a magnetic field, their vectors align with it, attracting each other. But just like in the case of diamagnetic materials, this interaction is so weak that it is almost unnoticeable. Now we can talk about stronger magnetic interactions: ferromagnets, ferrimagnets, and antiferromagnets. Let's start with antiferromagnets. I like to call them dumb magnets. They are usually oxides, for example hematite, iron 3 oxide, nickel oxide, or manganese 2 oxide. On the one hand, their structure allows for magnetic moments to align, but on the other hand, their moments align in opposite directions, cancelling each other. So they are magnetic, but in such a way that it is not magnetic. This can be easily represented with magnetic domains, regions in magnetic materials in which magnetic moments of atoms are aligned. They are directly tied to the microstructure, found in crystalline materials. In paramagnetic and diamagnetic materials, magnetic dipoles don't spontaneously align, so they don't form magnetic domains. Usually, instead of crystalline structure, their structure is amorphous. So, antiferromagnetic materials have magnetic domains, but inside, atomic dipoles are aligned in opposite direction, cancelling each other. In a magnetic field, their magnetization aligns with it, but they still cancel each other. Ferrimagnets are something in between antiferromagnets and ferromagnets. Their magnetic dipoles in magnetic domains are aligned similar to antiferromagnets, but they are not equal to each other. If we reduce them to one vector, it becomes smaller, and the corresponding force is weaker. They can spontaneously align, so they are attracted by magnets, and can be magnetized to create permanent magnets. One example is this simple ceramic fridge magnet. It is probably made of ferrite, ceramic iron oxide compound. And now, the last type of magnetic materials, the holy grail of magnets. Ferromagnets. Same as with two previous types, their dipoles in magnetic domains are aligned, but this time they are aligned in the same direction. So instead of cancelling each other, they strengthen. In the presence of magnetic field, they align with it, exhibiting strong magnetic force. Materials with ferromagnetic structure are the strongest magnetic materials. They are usually transition metals with free electrons, which allow for strong magnetic properties. Iron, nickel, cobalt, neodymium, all of those are used to produce magnets with considerable force. Until now, we only talked about how magnetic materials react to the magnetic field, but magnets don't need a magnetic field to be magnetic. Magnetic materials can be magnetized to become permanent magnets. To do this, we need to meet certain conditions. Ferromagnets have a few properties that can dictate how hard they are to magnetize and how good they are as magnets. Permeability, how good material magnetizes in response to a magnetic field. High permeability is necessary for magnets. Coercivity, ability to withstand external magnetic field without being demagnetized. High values are desired for magnetic materials. And remanence, how well a material can hold its magnetization after an external magnetic field is removed. For permanent magnets, high values are desired. But for electromagnets, it is usually not desirable. Those parameters can determine if magnetic materials can produce soft or hard magnets. In case of soft magnets, they often have high permeability but lower coercivity and remanence. Those materials can be easily magnetized, require less energy to be magnetized, but quickly lose their magnetization. Hard magnets also have high permeability, but their coercivity and remanence is higher than in soft magnets. This makes them relatively harder to magnetize, using more energy in the process, but also they retain their magnetization. There is also one more important parameter regarding magnets: temperature, and more accurately, Curie temperature. At this temperature, magnetic materials lose their permanent magnetization due to magnetic domains becoming disordered again. Generally speaking, higher temperatures make it easier to rearrange domains and make magnetic materials magnetized or demagnetized. So, to make a magnetic material into a permanent magnet, we need ferromagnetic or ferrimagnetic material. It has to have sufficient coercivity and remanence for domains to stay aligned. Then we need to apply a strong magnetic field to realign domains. Getting closer to the Curie temperature can make this process easier, and at this point we obtain a permanent magnet. Its aligned structure allows for creation of a magnetic field. A good example of a permanent magnet is a neodymium magnet. There is a high chance that you played with it as a kid. They are strong for their size and don't lose their magnetization unless heated to around 300 Celsius or 600 Fahrenheit. I should also mention one other type of magnets: electromagnets. Since magnetic and electric fields are tied together, we can induce a magnetic field by passing sufficiently high electricity through a wire. In fact, all wires when conducting electricity are magnetic. The magnetic force is just so weak that we don't notice it, but it can affect sensitive components and circuits. We can increase magnetic field by wounding the wire around a core made from ferromagnetic material. In this case, current passing through a wire creates a magnetic field centered in the hole at the center of the coil. The addition of ferromagnetic core, which aligns with this field, as I showed you before, can even further strengthen the emitted field. This interaction between current and magnetic field allow for quick change in polarity of electromagnets when the direction in which current flows switches. That's why electromagnets are used in electric motors, generators, speakers, and a variety of scientific equipment. And if you think about it, even the Earth is like a one big electromagnet. Movement of molten iron and nickel in Earth's outer core generates electric currents, which are responsible for the geomagnetic field. It shields us from solar winds and allows us to use compasses to navigate. So, magnets are everywhere. It is not a magic, just physics. Humans can produce various kinds of magnets and use them in many applications, from scientific instruments, electronics, industrial processes, to simple toys and items holding your notes to a fridge. All things around us are in some way magnetic. Most of the time it is just too weak to notice. If you want to learn more about atoms or how the temperature works, check out my other videos. Did you enjoy this video? If yes, subscribe and leave a like. Feel free to share your thoughts in comments. And see you in the next one.